And just a reminder that if you have any questions afterwards, we do have a microphone, and since this is being streamed, please use the microphone instead of just shouting. Thank you.
All right, well, thank you. Thanks for coming to the last session of the conference, everyone. Can't have a conference about the moon without some sample talks, so let's look at some rocks. So before I start talking about the chromite symplectites, I'll give you some background on Troctolite 76535. It's one of the largest and most pristine samples of the Highlands magnesium suite, and therefore it has been one of the most highly studied samples from Apollo 17 over the years. It's an olivine plagioclase cumulate with some minor OPX and other minor phases I'll talk about a little bit later. It's been dated thus far pre-Serenitatis at about 4.23 GA. And one of the diagnostic features of rocks, not only 76535, but most rocks that belong to the magnesium suite, is that their olivines are extremely low in nickel, cobalt, and chromium. And this is low compared to Mare basalt olivine. If we take a look at different lunar olivines, I'll walk you through this diagram. I'm kind of comparing apples and oranges here a little bit. But to look at Mare basalts first, we see a decreasing trend, decreasing chrome as we go down an Mg number. But olivine in the magnesium suite, as you can see here, has very low chromium for its high Mg number. And this star way down here, almost near the bottom, is 76535. Averages about 140 ppm chromium. Now, in the green triangles here, this is a little bit different. This is early lunar magma ocean olivine that we produced experimentally in our 2011 paper. Now, the reason I have this on here is because the early LMO olivine is hypothesized to be a rather large component of the Mg suite source material. So if we partially melt cumulus dominated by this olivine, chromium is slightly incompatible in olivine, so the partial melts will go up in chromium. And my point of this diagram here is that these partial melts will never crystallize olivine that is this low in chromium. So we have some sort of discrepancy here that we're gonna try to address. Let's see. Now, because like I said, the olivine in 76535 is very low in chromium. However, we also have highly concentrated amounts of chromium in the form of symplectites in 76535. And these consist of chromite, which you can see here, and this is backscattered electron images. Chromite is the very bright phase, and it also contains clinopyroxene and a low calcium pyroxene that you see here in the dark phase. Symplectites occur most often along olivine plagioclase grain boundaries, and they're oftentimes associated with these large intercumulus OPX grains that we see throughout the rock. So some of the questions that drove this study is why is chromium highly concentrated in symplectites 76535, yet the olivine throughout the rest of the rock is so chromium poor? Is there a secondary process that can explain the low chromium content of the Mg suite olivine, or is this a reflection of low chromium parental magmas, which that would then be inconsistent with their source materials being early magma ocean olivine? And then what do the answers to these questions imply about Mg suite petrogenesis? So we've aimed to reinvestigate symplectite formation to try to answer some of these questions. So there have been a number of symplectite formation mechanisms that have been proposed in the literature. And there was a lot of debate about this back in the 1970s. The first symplectite formation that was proposed was that these areas represent pockets of crystallized trapped intercumulus melt. And the source of chromium for this formation mechanism would simply be chromite that crystallized from this trap melt. The second formation hypothesis was a reaction between olivine and plagioclase. This is the model reaction from the CMAS system. It's fairly well understood, and it can be shifted to the lower pressures relevant in the lunar crust by the addition of iron and chromium to the reaction. Now, the two sources for chromium for this reaction have been suggested to be diffusion of chrome out of the olivine and also remobilization of cumulus chromite grains that form from the primary magma. Now, before we reassess each of those formation mechanisms, I'll give you a little preview of our observations and our data so we can keep everything in context. So we see symplectites and associated chromite veins that occur at or very close to olivine plagioclase boundaries. However, by far, most olivine plage boundaries in the rock are symplectite-free. And symplectites are also found, as I said earlier, usually in close association with large intercumulus OPX grains. We do not see any chromite in the rock that is included within olivine or that are clearly cumulus chromite grains. And olivine-hosted melt inclusions are chromite-free, and as I'll show you in a moment, their pyroxenes are extremely low in chromium as well. Additionally, we see other assemblages in the rock that we do think are representative of trapped melt pockets, and they contain only small amounts of chromium, typically in the symplectic texture. So looking at the trap melt hypothesis first, this has been crystallization of symplectites in layered intrusions has been documented in the terrestrial setting. We see symplectites with FeTi oxides from Skaergaard, for example. This hypothesis, however, I do not believe is supported by the textures, and this is for two reasons. First is that this requires significant adcumulus growth of both olivine and plagioclase from the melt pocket, and symplectites do not contain other minor phases that we see associated with melt pockets. So here's a backscattered electron image of a symplectite. It's been darkened, so you just see the chromite. As you can see down here, we have an olivine plage boundary that's partially delineated by a chromite vein, and we can trace this remnant of this chromite vein right through the symplectite. If this symplectite was a crystallized trap melt pocket, simply that boundary would never have existed in the first place. So I think that's strong textural evidence against this being a crystallized melt pocket. Additionally, when we find other assemblages in the rock that we do think are trap melt pockets, they look nothing like the symplectites. As you can see here, this is a large apatite marylite intergrowth surrounded by plage and a bit of olivine here, but we also have other phases such as bdelliite. We find zircon, iron nickel metal, 2 pyroxenes. So we think that these assemblages are more representative of trap melt pockets rather than symplectites. The second hypothesis was that the source of chrome for the symplectites was simply chrome that was in an originally more chrome-rich olivine that has diffused out. However, when we get down to the very low oxygen fugacity conditions relevant to lunar magmas, we have a very high chromium 2+ to 3+ ratio, with 3+ being the form of chromium relevant for chromite. Now this the Cr 2+, 3+ ratio can even go over 1 at magmatic conditions. So what we need if diffusion was going to be a viable mechanism is a chromium oxidation reaction, where chromium 2+ plus iron 2+ goes to trivalent chromium. Now the other product of this reaction is that if it was occurring, we should be seeing a large volume of iron metal in or around the symplectites that we simply do not observe. Now, additionally, most of the olivine in the rock is not anywhere near or in contact with symplectite assemblages, yet it is all uniformly depleted in chromium. Let's see what I have here. So first I'll show you some melt inclusion data, then I'll talk more about the olivine in contact with symplectites. So looking at pyroxenes in 76535, you see here that we have large intercumulus pyroxenes and our symplectite pyroxenes that are much more chrome-rich than our melt inclusion pyroxenes. We think that the pyroxenes and the melt inclusions probably are more representative of the chrome content of the parental melt, which seems to indicate this was very low in chromium. Additionally, a backscattered electron image of some assemblages in 535. We have a chromite vein here with some symplectic texture along an olivine plagioclase boundary, but this picture even of itself is not representative of the entire rock. Most of the rock consists of these very boring boundaries where we have olivine and plagioclase in contact and nothing else for sometimes millimeters around. If chrome was diffusing out of the olivine to form the symplectites, then there should be chromite veining along all or most boundaries, or at least we should have symplectites in contact with all of the olivine in the rock, and we simply just don't see that. So the last hypothesis was that we had pre-existing cumulus chromite grains that crystallized from the parental magma, and that these then subsequently reacted with the surrounding olivine and plagioclase to form the symplectites. And this provides the very obvious constraint that the original parental magma must be chromite saturated. Now, I think this is argued against by the low chromium content of our melt inclusions and the fact that there is no chromite found in olivine-hosted melt inclusions throughout the rock. And when we look at the chrome content of the olivine that we have, it seems to be inconsistent with formation from a chromite-saturated magma. So I'll see if I can walk you through this diagram here. In this diagram, we've modeled the total Cr2O3 content of olivine in equilibrium with a chromite-saturated magma as a function of FO2. So that's what these red and blue lines here represent the chrome content of olivine in equilibrium with a chromite-saturated magma at different temperatures. And I've marked the lunar oxygen fugacity here about iron wustite -1. Now this orange line down here is the maximum reported Cr2O3 content of olivine 76535, and this is actually about a factor of 3 larger, higher than most of our analyses here. And at typical magmatic temperatures at lunar oxygen fugacity, the chrome content of 76535 olivine is just simply not consistent with crystallization from a chromite-saturated magma. Not even close, as you can see the discrepancies here. So we feel that this argues against there being originally primary cumulus chromite grains in 76535. So this leads us to the conclusions that internal sources of chromium are inconsistent with multiple textural and geochemical observations from the rock, and that we feel that open system addition of chromium to 76535 is required to explain the symplectites. For time factors, I won't be able to go through other models that we've considered, but various factors to us rule out models that involve differential settling of chromite from higher in the pluton, and also infiltration by an exogenous fluid. The model that we feel best fits the observations is a model of infiltration metasomatism of a chromite-saturated silicate melt. And I've got some cartoons that show that process here. So we've got in this box up here, 76535 in the post-cumulus stage. We have infiltration of an exogenous melt. We feel that since the OPX grains overlap in chromium content with the symplectite pyroxenes, that these OPX grains probably formed as a reaction between olivine and SiO2 in the melt. Many lunar basalts, the liquidus phase is actually a chrome-rich spinel. So when this melt infiltrates the rock, it cools and crystallizes chromite. This chromite is deposited along olivine plagioclase boundaries, and it is out of equilibrium with that assemblage. So the symplectite formation reaction occurs, and that forms the symplectite in 76535. I'll toss up my conclusion slide here, but I just want to draw your attention to the last point here. And this is a bit speculative, but if our model is correct, I think this point is true. If we have intimate interaction of migrating melts with lunar crustal lithologies not long after the solidification of the magma ocean, I think this has the potential to keep these lithologies, the ferronorthosites and the MG suite, hot for a long period of time, and may actually delay closure of some of the radiogenic isotopic systems. So if we're correct, this may help explain some of the age overlap between the ferronorthosites and the MG suite. Thank you.
Okay, we have about a minute for questions. Larry?
Yeah, very nice presentation. Clive and I are sitting next to each other. Back in the 80s, late 80s, we were working together, and we came up with this thing that we had this silicate liquid immiscibility, and we have a separation of K-frac and refrac.
Yep.
And the K-frac was more like granitic, felsic, and the refrac was a very, very low viscosity thing that could possibly be doing metasomatism. And we proposed that way back when. And I think you might be seeing that because it would, the refrac is very high in iron and obviously contains some chrome. that might be some kind of, what you're seeing here, and I think we're seeing a lot in the, we've got primitive mantle rocks, primitive highland rocks, northosites, and yet they have a very advanced type of rare earth pattern. And we were proposing then, and we still hold true, I do anyway, that this is a refraction. And what you're seeing is metasomatism, which we haven't thought about on the moon because we knew it was dry.
Right.
Okay.
And, you know, the effects of metasomatism on the moon are not going to be as obvious as they would be on Earth. We don't have the water, like you say, so we're not going to have veins of, you know, chloroplite running through the rocks. We actually did consider the refract as a possible metasomatic agent for 76535. However, I couldn't reconcile that with what I would think would be low chromium contents in that melt. We've had extensive ilmenite fractionation in the magma ocean. That ilmenite is going to take up a lot of the chromium that's probably left in the magma ocean. So while I don't think that process is wrong, I probably tend to agree with you that a lot of that is occurring. I'm not sure that that particular melt would be appropriate for this case.
You don't have to have it chrome saturated in order to have a residue of chrome.
Okay, we're going to have to move on. You guys can